Okay, let me give you a snapshot of what the individual groups have been working on, and I'll sort of highlight some of the arguments that were made. In that way, we'll discuss the main results here, and I think we'll still have a couple minutes, possibly at the end, to at least set the stage, if not outright prove, the theorem that we've been hinting at, which is 824. Which is also, again, one of these homework questions that you have. I'm sorry, 823, one of these homework questions. Okay, let's take a look at the snapshot here. There is a pairing of 817, 818, and 819 that all, I should say, 817 and 818 are lemmas that lead to theorem 819. And theorem 819, the statement of the theorem is not copied here, but I will write, if a set S is compact, then S is closed, right? And this is huge. Back in 816, we said if a set is compact, then it is bounded. And so now we will have two different criteria that follow from compactness. We have that it must be bounded and it must be closed. And the argument that this group made over the course of these two lemmas and a theorem was as follows. If a set is not closed, then it must necessarily not contain all of its own accumulation points. And so there must be at least one accumulation point P that's an accumulation point of the set, but is not in the set itself. What the lemmas did then is the lemmas constructed a really interesting open cover, specifically an open cover that sort of looked like it was covering everything except the accumulation point in question, sort of the outside, this outside open area. But it constructed this intricate, technical, clever open cover that did not admit a finite subcover. So what they really showed is if a set is not closed, then it cannot be compact, because they can construct a particular clever open cover focused on that accumulation point that does not contain a finite subcover. And again, the details, are numerous and slightly technical, but that is the main idea there. Next, we had group 2 that was working on theorem 820 and 821. They had a theorem, I should say their main thrust was 821, which was this statement right here. Specifically, if we have two different sets in a relationship with each other where we have T is a subset of S, if S, the larger set, is known to be compact, and T, the smaller set, is known to be closed, then T is also compact. And the argument here, right, it was a very clever argument. The argument was to show that this set is compact, we had to take an open cover, arbitrary open cover of this set, and somehow show that that there existed a finite subcover. To do this, this group took the open cover of the smaller set and expanded it to create an open cover of the larger set, right? So they took the smaller set's open cover, union another open set that sort of got at this larger set S, to create an open cover not just of the small set, but in fact an open cover of the large set as well. Then they use the compactness of the large set to get a finite subcover, which in turn they could use to show that there was actually a finite subcover of the small set to begin with. Right? So I should say group 1 or group 2 and group 3. Let me know if I'm mischaracterizing anything, but as I understood your argument, you were saying that we took an arbitrary open cover of the small set, added on an additional open set to create an open cover of the large set, reduced it to a finite subcover of the large set, and made an argument to say that that must have also induced a finite subcover of the small set. So again, I think a challenging argument, but and it used, I should say, theorem 820 in a meaningful way. Yes. So now we have this result about relationships between compact sets and smaller closed sets. And that was group 2. Group 1 had a single argument, but it was absolutely the most technical argument of the bunch. Group 1 had to address the Heine-Borel lemma, which gives us an explicit example of a compact set, and it's our only one that we have. The closed interval from A to B is a compact set. And so that is in this theorem 822 down here. The argument there was, again, very technical, and so I'll give you a quick overview. In short, they took an arbitrary open cover of the entire set from A to B. They had to show that this entire set, or I should say that open cover induced a finite subcover of the entire set. But to do that, they started at the left end, A, and created some sort of bootstrap argument to say that you could create this finite subcover. So starting at A, this is the point A, they found an open cover of A, right? Or I should say they found a finite subcover that covered at least the point A. They then said that not only does that cover A, but it covers up to some A plus epsilon. So there's a finite subcover, maybe not all the way from A to B, but at least from A to A plus epsilon. Okay, and then they said, can it stop there? Or can we extend that further? Well, if I take a second open cover, or a second, I should say a second open set in the open cover, I can extend past the point A plus epsilon and get even further, right? And I can continue to add on these open sets in some meaningful way. And the question was, can we get all the way to B, or do we add on this open cover that gets stuck somewhere? And they made an argument by contradiction, which again was a little technical, and I don't think we'll be able to get all the way into it. An argument by contradiction that said, no, we can't get all the way to 813, or we can't get all the way to, if we can't get all the way from A to B, then we would get stuck somewhere. But through a clever contradiction argument, we can't actually get stuck somewhere without being able to, again, add on an extra open set and extend it a little further. So the details are in the proof, and I'm not quite doing it justice, but in this bootstrappy way, they were able to show that the entire interval from A to B was coverable by a finite subcover of their arbitrary F, and therefore that A to B was compact. Now, that was a quick overview. So let's get into the question that's on our mind, which is based on all of that. I'm going to scroll way down to the bottom, which is, I guess, right here. Theorem 823, the Heine-Borel theorem, actually gives us the characterization of compactness that we use most often, right? It says S is compact in R if and only if S is closed and bounded. So we get to leave behind the challenging definition of open covers and finite subcovers and talk about it being simply closed and bounded. And there's a very slick argument, which, if you'll permit me, I'd love to sort of talk through with you. The argument is actually to use the results that you all have compiled here. To say this is if and only if S is closed and bounded. We have shown that in the forward direction, if S is compact, say this is proof, if S is compact, then S is closed and bounded. How do we know that it's closed? What was the result that told us if S is compact, then S is closed?
816.
816, yeah, thank you, Joe. That's 816. And bounded. And that would be bounded, I'm sorry, bounded is 816, right? Closed, Joe, that's the one you all were working on. Yeah, that was 819, thank you. So in one direction, we have this down. If S is compact, then S is closed and bounded. In the other direction, if S is closed and bounded, what then? we can show that this is compact in 2 steps. Number 1, if S is bounded, what does it mean to be bounded? What does it mean for a set to be bounded? Right? Well, if it's bounded above and it's bounded below by 2 numbers. So every element of S is between this number and this number. Well, let me call this number A and this number B, and we can say that S is a subset of some interval from A to B. Since it's bounded between 2 numbers, and therefore it's a subset of the closed interval between the 2. But we know A to B is a compact set. How do we know that's true? What was the result there that said that was true?
2.8.22.
Yeah, that's exactly right. That was the Heine-Borel lemma. That was the one that that group 1 talked through. 8.22 says that A to B is a compact set. So S is closed, and it's a subset of a compact set. Now we can turn to group 2's result, and what does that tell us? So by 8.21, S is also compact. It was the closed subset of a set that we know is compact, and so it is also compact. And that's the whole proof. So this actual really challenging, really powerful theorem can be proven really simply and quickly just through a couple key uses of some of these other theorems that we've spent the week developing. And now we have this excellent way to describe compactness. All right, let me sort of stop there, but say, are there any questions about that final argument? I was really hoping to be able to